Hello everyone, thank you for being so patient. It took me a while to get the next video up. So what we're going to talk about today is a little bit more on those alpha, beta, unsaturated carbonyls. They looked something like this. All right. And it was called an alpha beta because with respect to the carbonyl, this first carbon here is alpha and this carbon up there is beta. Now, this can be on a lot of different types of molecules. You have an aldehyde here. You can use a ketone, an ester, or an amide and just have that alkene right next to it. And we also kind of went over the fact that you have good conjugation through that whole system there. And if you want to go back and look at a previous video where I showed you the MO orbitals and HOMO and LUMO and that sort of thing, go right ahead. What I want to do right now, though, is show you the chemistry of this from a slightly different perspective. So there's our neutral molecule. What we're going to do is we're going to go into a series of possible resonance forms. One of the resonance forms happens this way. When one of the pi bonds break, the carbonyl pi bond breaks and the negative charge ends up on the oxygen. So what you have now looks like this. Now, this isn't that shocking because if you'll remember, we've always been saying that carbonyls have a partial negative charge on the oxygen and a partial positive charge on the carbon. But we're not quite done yet because there is a way to resonance stabilize that cation. And it would look like this. Now, what I hope you would see from this is the fact that realistically in these alpha beta unsaturated carbonyls, you have two electrophilic sites. Because when you write out the hybrid down here, remember to do a resonance hybrid. Whoops, that was a mistake. To do a resonance hybrid, you draw in the sigma bonded skeleton of the molecule. Dashed lines wherever there is pi bond density, and wherever there is a charge, you put a partial charge. And what I would like you to see on this particular example is we have two potentially electrophilic sites. Two potentially electrophilic sites. So now what we can do going forward is we'll talk about what kind of nucleophiles would prefer the carbon down here on the left with the partial positive charge. So let's look at something that's called a conjugate addition. Also called a Michael addition. Most likely because if somebody named Michael probably first developed it. Although it could have been Michelle, you never know. All right, so let's take a look at this. This is what the molecule would look like before we do anything to it. So for a conjugate addition, what will happen is the nucleophile will attack that carbon. Now, I'm going to go ahead and rewrite this on this page because you don't need necessarily to flip back. This was the resonance hybrid. We have a partial positive there, and partial negative there. All right? So, nucleophile would attack that carbon. The pi bond breaks. It swings over here. Sorry, I wanted to use yellow there. Pi bond breaks, swings over there, and then breaks open the carbon-oxygen pi bond. So our next step is this. The nucleophile has added, and we have our negative charge on the oxygen now. So all we need to do at this point is add a little bit of acid. It even can be mild. And you'll get this. Which hopefully by now all of you will recognize that this is an enol. So you will get a tautomerization back to this. This is how a conjugate addition works. Is you add a nucleophile to the beta carbon with respect to that carbonyl. So, real quick, what I'd like you to recognize here is that this is your alpha-beta unsaturated carbonyl. I don't think any of you are going to be too upset by that. And like I mentioned earlier, we have two electropositive sites. So what we need to do now is differentiate between what kind of nucleophiles would go for this carbon, and we would call that a direct addition, and what kind of nucleophiles would go for the conjugate addition. And the list isn't that bad, to be completely honest with you. The list is really not that bad. So what we're going to do is we're going to go ahead and divide these up. All right? So, direct addition. Direct addition, where you go right for the carbonyl carbon. We're talking about hydroxide or water, alkoxide or alcohol. And I will remind you, these two only happen when you've got an acid involved, or the electrophilic pathway. Also, Grignards, Wittigs, and alkyl lithium agents. All of these will do a direct addition. This is what you've seen before in terms of nucleophilic attack at the carbonyl carbon, where the nucleophile would do this. Now, for the conjugate addition, it's a little bit different. The nucleophiles for the conjugate addition consist of double enolates. Allow me to explain that. Something like this, where it's a diketone and you have a negative charge in between the two carbonyls. It could happen something like this, where you've got some kind of malonic ester. That will also work quite well. So will a ketone ester. Hopefully this wouldn't have to be explained, but I will in case it is. That will also do a really nice enolate reaction. So will this one. Using a nitro group. And finally, Gilman reagents. The organocuprates that we've talked about before. All right, I'm going to stop this video now, and we're going to come back and we're going to look at some options here and some of the types of chemistry that you can do. So just for those of you who like to keep up, I would imagine we are going to finish this chapter in the next video or two. And then we are going to go all the way back to chapter 18. And we're going to finish the semester with chapter 18 and 19. All right? So have a good day, and I'll talk to you soon.